All right, well, it looks like this is everybody who's showing up. So let's get started. Who's got our first question? Come on, Christina, I know you got something for me.
I'm trying not to monopolize every single class.
Don't worry. It always takes somebody to get the ball rolling.
I'm happy to do that. I do have one question. It's going to go back to the final project, if that's okay.
Sure.
So on the final project, I know we talked about this on Monday a little bit, and I apologize, but I just want to make sure I understand like how you're wanting us to approach this. I mean, it's really like a thought project. Like when I'm thinking about the variables and all the different stuff, I mean, you kind of just want me to like mock up what I would be studying in terms of like an interventional study. Like I think my dissertation will be an interventional study actually. So I'm thinking of it through that lens, but you want me to literally like just kind of give you a very brief background on it, the problem you're trying to solve in terms of like the research question and then the data you would collect to address the research question. Is that sort of how I should think about it?
That's exactly it.
Okay.
Yeah, just think of it as a very small, pared down, kind of dry run for your dissertation.
Yeah. Can I ask you, like, not really, I'm obviously not going to get into this. This is more of just a statistics methods question for you. Just in general, like when you would approach something where like a digital therapeutic where you needed to account for a number of different confounding factors and variables, right? So like you would have to adjust for comorbidities, recent health history, right? You want to normalize that population as much as possible so you can make inferences about the effectiveness of the intervention. Correct. What type of statistical analysis are you doing when you're adjusting for like multiple confounding variables? Like what I mean, I know that I'll get that in the next statistics class likely, but I'm just curious like how you approach that. I mean, I know there's like ANOVA and all these other things, but I'm just curious like how that typically is done.
Well, it depends on A, the type of data you have, B, how the confounding variables are related to the data you're trying to measure. Basically, every situation is treated differently, but usually, often you can control for or eliminate a vast majority of your confounding variables just by adjusting your sampling technique. And then if that's not possible, then usually you can weed them out with like multiple regression and those kinds of things. But sometimes you just can't get rid of them at all. And then, you have to run the data and then you just look at your findings and then you have to kind of, take them with a grain of salt and report back to the reader that, by the way, there are these possible comorbidity, confounding variables, whatever you want to call them, that we weren't able to control for, that kind of thing. And then that's when in your dissertation, there's always a section called, suggestions for further research. And that's what you would talk about in that section. We're going, well, going forward, I would love to either, do it myself or see someone else be able to blank and then talk about how you would maybe design a study differently that would have a better chance of getting rid of those confounding variables.
Yeah. I think what always trips me up is because when I think about like selecting a sample population that controls for certain things, then I always say, how is that not like a purposeful sampling technique, right? Like if you're selecting for certain things, like by default, you're not necessarily testing the generalizable population, because in the truest sense, you would get whatever came to you, right? Like if you're really doing truly random sampling, but then it's just a question I've always had. Like when we hit this all the time, like when we're trying to do things around like this interventional stuff for work, you always have to talk about the things that could have interfered with your results and make them less generalizable is basically what you talk about.
Absolutely. But think about it this way, you always do sample massaging. I mean, in the medical field, they do it all the time when people, sign up or volunteer for to be in some sort of clinical trial, they will deny people all the time because they have a certain characteristic that they don't want in their trial, or they don't have a certain characteristic they do want in their trial, right? Because, if you want to figure out if a weight loss drug works, you don't need a bunch of skinny people, right?
Yeah.
So,
True.
and if you're trying to figure out if something helps with, high blood pressure, you need people with high blood pressure, right? So it would be perfectly legitimate to be able to massage your sample that way.
Sorry, Dr. McBride.
Yes,
How
Mr.
would I handle the scenario of like engagement, improving engagement in e-learning, and turn that into something that would be normal probability rules to solve?
Well, it all depends on how you're measuring engagement. And I would imagine you're probably measuring engagement through Likert scale questions, maybe, or are you able to actually measure how much time they're spending on task doing something, right? So
I can do both. Likert scale questions would be great, and also amount of time they're spending by looking at the log.
Yeah.
Of a system, how much time they're logging in a class. So how would I do either approach?
Well, if you're measuring how much time they're spending on tasks through the logs, well, remember, time is a measured variable. That's a continuous variable. And by definition, that will have a normal distribution when you do a sampling distribution of it, right? So obviously the population of times themselves might not be normally distributed, but the central limit theorem tells us that if we sample from that population with a sample size that's at least 20 or bigger, then we're going to get a sampling distribution that is a normal distribution, and then you can apply all of these probability theories to them that way. So you'd be able to do that with that variable or any other variable that's a measured variable. With the Likert scale things, those are just ordinal levels. So we truly in the purest sense of a statistical form, you cannot really do any statistical analyses on Likert scale data other than frequency counts. However, it has become a fairly acceptable practice to treat Likert scale data as if it were ratio level data instead of ordinal level, and run all sorts of statistical analyses on that data, knowing that the results are inherently flawed because the data itself is not truly ratio level. But it's one of those things that everybody does it because everybody wants to know more about their Likert scale data than they can get from just Likert scale data. So that's the problem with that. Now, a good way to get around that is you can, as the researcher, you can define a scale score that is based on Likert responses. And then basically what you're doing is you yourself are coding those Likert scale responses onto a numerical scale based on prior knowledge, prior research, your own expertise, whatever, a combination of the three. So what happens is you now decide how much weight to give a response, and you put it on a numerical scale. So you can now treat that data as actually being ratio level data because you have actually coded it in as ratio level data. Now, that too, of course, has its problems because it's subjective. You are the one making the decisions about what those numbers should be, and you're not truly technically measuring something other than you're measuring it yourself. It's not like you're taking out a ruler and you're measuring something. You're basically putting a measure on something that really isn't being measured. But that is another technique that is often used with Likert scale data that enables the researcher to run more statistical analyses on it because they can now treat it more robustly as ratio level data.
AO, I know we were going to try to connect this week, and I apologize because work is just brutal. I don't know if this is like helpful for you or not, but there are ways you can look for validated instruments to gauge engagement rates on different digital, like we do them in healthcare. So we have something called a patient activation measure. I'm actually going to talk about it in this response, Dr. McBride, but it's a validated measurement tool that you
Yeah.
can do pre and post that actually gives you, it's not Likert scale data. It's actually like a continuous data set that you can actually gauge a level of engagement using that activation. We use it for patient activation. But the other thing that you could look into is if you wanted like quantifiable data that helps you understand whether somebody's engaging with a digital app for learning as an example, I would look into like the UI UX fields because they do a lot of things like clicks per screen and did you follow an action and things like that. And then you have like a little bit of a more, like the data's coming off the digital device. We can talk. I know you wanted to meet with me at some point and we can get some time. This week was really bad for me, but we do that a lot at work when we're trying to understand if people actually use this stuff.
Yeah, that's great. Of
Thank you so much. That's very helpful, Christina. Thank you, Dr. McBride.
course. Anybody else? I know we had a couple people come in late. Any other questions specifically from the homework or the final project?
So, Dr. McBride, I also have the same question about my project, my dissertation. So, I would be measuring faculty motivation, increase in motivation in teaching online
Okay.
due to COVID.
Sure. How are you going to measure it?
So again, it's going to be a qualitative study, and I'm going to measure it based on their has anything changed because of what are the factors that motivate them. So some of the factors are like flexibility in teaching online.
Okay. But I mean,
And
specifically, what kind of data are you going to collect and how are you going to collect it? Are you going to interview them? Are you going to give them a
interview
survey?
them. Yeah.
You're going to
So
interview
I
them?
was thinking, I was thinking mixed method, but most of the people are discouraging me because I was thinking maybe first I can get the survey out. That way I can have most of the population at college because I work at a college. So I can have most responses through survey and then pick some selection and interview those faculty members. So that's what I was thinking, but everyone's saying mixed method could be a little bit more tedious, so do qualitative. So qualitative would be based on the interviews.
Yeah, I mean, there's nothing wrong with qualitative data and there's nothing wrong with qualitative research. It does, however, severely limit the types of research questions you can ask, and it obviously severely limits the type of analyses you can run. But it doesn't mean that it's any less useful than anything else. You're going to get a lot of really all you can do with that data would maybe do some frequency counts and some chi-square analyses and things like that, but that would be it. If you asked them questions that would elicit numerical responses, like how many hours a week did you have to spend doing this, and how many times during the semester did you have to do that, and those types of things, then you could have some numerical data that you could then run some statistical analyses on them. And even if you didn't want to do that in a survey, you could still ask them those types of questions during the interview. So there's no reason why a qualitative study can't have some numerics in it that you could run some basic statistics on it. And then, yes, of course, it would be considered mixed methods, but it would still, at the heart of it, be a mostly qualitative study. It really comes back to a well-defined research question will guide everything. You really need to define the problem, the solution, and the research question very well, very thoroughly, and then that will guide you as to what kind of data you need to capture. And then once you know the specific kind of data you need to capture, that will then guide you as to how you capture it. Oftentimes students put the cart before the horse a little bit too much, and they think about, well, I want to do these interviews and I want to run these surveys to gather all this data, and I have to stop and go, yeah, but why? What exactly are you trying to answer? Because you better know that first because that way you're gonna know exactly what kind of questions you need to ask, and so that's what's really important. So make sure you nail that down before anything else.
So for this project, in that case, because I still don't have a very well-defined questions, I don't have the very well-defined method. Most of the things I'm thinking are gonna be countings, so they're gonna be discrete data, not continuous.
That's fine. You can still run statistical analyses on discrete data. I mean, there's things that you're supposed to do to account for it, but just like people treating Likert scale data as if it was ratio level, a lot of analyses are run on discrete level data as if it were continuous. So it's kind of just an accepted thing. All you have to do is make note of it, that although that, I'm aware that this data is discrete, so I'm aware that the results are, taken with a grain of salt, so to speak, but here are the results anyway. It's that kind of thing.
So in for this project, are we not supposed to have the continuous?
Well, if you're talking about for our class, you don't
Mhm.
need data at all. This is a complete thought experiment. So questions 1 through 5 is basically just trying to get you to do what I suggested, as far as try to narrow down those specific questions, right? Try to narrow down the problem, and well define the problem, or define well the problem, and then try to define your solution really well. Try to come up with a better, defined research question or questions. And then from there, that'll give you an idea about the possible variables and the things that you want to collect. They don't have to be continuous, it just asks if they are, right? So just discuss if they are continuous or not. And then for part 5, you would describe some of the methods that you would use to analyze the data, which of course all depends on what kind of data you have. And then question 6 is completely different. It's not related to 1 through 5. With question 6, you're now supposed to make up. So if parts 1 through 5 didn't give you a continuous variable, if it did, then go ahead and use it for part 6. If you don't have a continuous variable in your scenario, then for part 6, just make up a continuous variable, make up its distribution, right? So here's my continuous variable. The population has a mean of this and a standard deviation of this. Now, based on that, if I wanted to calculate the probability that, one randomly selected individual has a score of blank, this is how I'd run it. Here's a graph showing, a graph of a bell curve showing what it would look like pictorially to be, greater than something, because that's the first part. And then for the second part, here's another graph showing what it would look like if we were trying to do the probability of being less than a specific number. And again, just pick whatever that specific number is. And then for 3, here's a picture of what it is to be in between two things, right? And then, and then for 4, I'm going to talk about a percentile question, which you can then also still, do a picture of a graph and say, here's, here's a little picture with a little shaded region that shows being in the top, 10%, or, being in the 75th percentile, or whatever it is you want to, because again, you're making it all up for that. So those are based on a fictitious variable with fictitious data that could be related to what you have in 1 through 5, or it could be something completely different.
Okay, so it doesn't have to be from first 5 questions.
No,
first 5.
no, not at
Okay.
all. Yeah, no, because your research could be in such a way that it's not going to produce any continuous variables.
Okay,
And rather than force you guys to come up with a scenario that will have a continuous variable, I thought it would be more helpful to have you guys run questions 1 through 5 as if it was your dissertation, so it can get you thinking more clearly about your dissertation. And then for part 6, if yours doesn't have a continuous variable, then that's where you're just going to make one up. And it doesn't even have to be related to what you did in 1.5. Just come up with a continuous variable. I don't care what it is. Hell, use weights or heights or whatever, right? And then just go from there.
Okay, and when you said graph, that's we can use StatCrunch normal distribution, right?
Oh
And
God,
then,
yes. Yeah. If you have StatCrunch, then you can get graphs out of that thing lickety split beautifully and easily. But if you haven't paid for StatCrunch and you don't want to use StatCrunch, you can either find other graphing tools online or draw them by hand and scan them or take a picture and put them in that way.
Yeah, StatCrunch calculator, that's for free. For
Yeah.
others, there is a for price.
Oh, I didn't know they had a StatCrunch calculator.
Yeah, it is there, but that's the only one free out there.
Oh, I didn't know that existed. Okay. I always just
Yeah.
went to the StatCrunch website, logged in, and then went to Stat Calculators normal. But there's a website just called StatCrunch Calculator.
Yeah, I just searched for the StatCrunch calculator. StatCrunch I was looking for, and then it took me to this website for StatCrunch where I had to sign up. Even though I sign up using my EDU because I work at a college, um, never got the invitation to open an account. But then there is a StatCrunch calculator, which is exactly the normal distribution.
Oh, perfect. Okay. Well, that's great. That's good to know. Oh, thank you, AO. That's awesome. Yeah.
If we I have a question about part 1.4 also. If,
You talk about
since we,
in the
uh-huh,
this one. Yeah.
yeah.
Okay. So this question is kind of a multi-step process. So the first thing we have to do is we have to figure out the probability of a family actually purchasing more than 4 freights, based on the New Walt data. So that means it's actually easy. All you have to do is add the probabilities of 5 freights and 6 freights. So for instance, if we go to our data, nope, that's part 2, part 1. So here's freights, right? And probability of freights. So number of freights has to be probability of getting 5 or 6, which is these right here. And you can see that if we add those together, the probability of a family buying more than 4 freights, because more than 4 just means these last 2, is literally just 5%, 2.5 plus 2.5. So that's the first thing we need to do is figure out, okay, the probability of a family buying more than 4 freights is 5%, because this question says, right, that you've got this list of information for 6 families only. Of these 6 families, 5 families purchase more than 4 freights. So using this information, calculate the probability that at least 5 of 6 German immigrant families purchase more than 4 freights. Well, that's a binomial, right? If you have a set of 6 things, 6 families, and you want to know the probability that at least 5 of them did something, well, then you have to know the probability of that something happening, because that's your probability of a success. Because this is a yes or no question, right? Did they buy that many or did they not buy that many, right? So that's a binomial. If it's a binomial situation. So the first thing we have to do is calculate the probability of a success. Well, a success is buying more than 4 freights. According to the New Welt data, that's a 5% chance. So our probability of a success is 5%. Now, based on that, all you have to do is calculate the probability that out of a sample size of 6, i.e. your n now is 6, right? For a binomial, n is your number of trials. What's the probability that at least 5 of them bought more than 4, i.e. at least 5 of them had a success. So remember that when we want to do at least 5, we would actually have to do a binomial with x equals 4, right? P would equal 0.05, and then n would equal 6. And we would do a binomial CDF. This would give us, right, the probability that the number of families that bought more than 4 freights, because buying more than 4 freights is what it means to have a probability of 0.05. This would give us the probability that that the number of families that did that was less than or equal to 4, right? So 0 through 4. So if we did 1 minus that, that would give us the complement, and the complement of 0 through 4 is 5 or 6, which is what we want, right? To be at least 5 of the 6 people bought that many. When you calculate that, you're going to get a number, and if the number is really, really small, then it's unlikely that this set of 6 families actually came from the New Walt stuff. If it's, at least close to 5, then you could say that it's probably, it could be, you know, from that data. But if it's, you know, really, really small, then chances are it's different data.
So this is not less than equal to 4, right? So it's more than 4.
They
So that
want to
means
know,
it's
they
5,
want to know more than 4, which is why we would do a
5,
CDF
6.
of
Okay,
4.
so
Yeah. Yeah.
okay. Yeah, this question is is the most difficult. Like the whole scenario is very difficult to understand.
Yeah.
Doesn't seem like normal English.
Yeah.
Can I ask a question on this? I think this is what I'm struggling with. Like I got the answer, but I just want to make sure I understand why you can apply the probability distribution from the new wall to calculate the probability for this. Like why, can you help me
Well, it's
understand that?
because the question is trying to determine whether or not this data came from the new wealth or not. So if you apply the probability distribution of the new wealth to this data and it fits well, then it means it's probably from the new wealth. But if it doesn't fit well, then it means it probably isn't. That's why.
So what tripped me up on that is similar to from a populate, like if the
Right.
question read, if this came from the New World population, then that would have made complete sense. I could not understand why you would use the probability distribution from New World if it was, I mean, I understand now. I get it now. But
Because
thank
if
you.
it was similar to it, that would mean it would have a similar probability distribution. So
Got it.
that's why.
Got it. Okay.
So you said it's like the probability. Is it like less than 1%, 2%, or very, very small? Like what would be the probability that it will not fit? It will not come from New World.
Well, in my opinion, because based on the New Wealth data, here, the probability of any one family buying more than 4 freights is 5%, right? Pretty small. So the probability of that out of 6 families, 5 purchased more than 4 freights seems pretty damn unlikely to me. I mean, just from, so the idea is that if this was a likely scenario, its probability should be fairly large. And when you run the data, it's going to be tiny. Usually the idea is if we treated this as if it were a hypothesis test, kind of the standard error for a hypothesis test is 5%. Anything with a probability greater than 5% is considered likely enough that we don't have strong enough evidence to reject the null hypothesis, which is, you know, that things are the way we originally say they are. So we're claiming that we think this is similar to the New Wealth data. So we would run the hypothesis test, we would run the data, we would get a probability. And if that probability was 5% or bigger, we would say, okay, it fits well enough that we don't feel strongly enough that we can say, we're going to reject that null and say that it's probably more likely that it comes from a different population. But if it's smaller than 5%, then we say, well, since there's less than a 5% chance that this data actually came from a population similar to the New Wealth, then we're going to say we feel, you know, validated enough that we can probably say that it most likely came from a different population and therefore it's not similar to that. Well, you know, I don't even have to run the data to know that that's crazy, because, you know, if the probability that one family buys more than 4 freights is only 5%, well, then I know multiple families is going to start making it less than 5% because that's how a binomial works. So there's no way in hell this comes from the new welt data, because 5 out of 6 do it. Oh my God, there's no way. And in fact, when you run the data, you will get an extremely small number. And that, you know, that kind of numerically verifies what your instincts should already be telling you, that, you know, if there's only a 5% chance that any one family is going to buy more than 4 freights, then if you had a random sample of 6 and 5 of them bought more than 4 freights, you just won the lottery, because, you know, that's basically getting a 5% success, you know, something that has a 5% chance of happening. It just happened 5 out of 6 times. That's ridiculously small. You know, think about it as having, this would be like a 20-sided die, right? Because then if there's a 20-sided die, each side has a probability of 5% of coming up, because 20 times 5 is 100, right? So that's akin to saying, I'm going to take a 20-sided die and I'm going to roll it 6 times, and 5 out of the 6 come up the same damn number. Does that sound likely to you? Right? So that alone tells you that it's probably not from the new welt data. But then we run the numbers and get an actual probability, and that actual probability is going to be very, very small. And that's what gives us an actual kind of numerical support to what our instincts already tell us should be the answer.
Okay, thank you. And then number 5, what
Mhm.
additional points? Discuss any assumptions. So what are you looking for in this answer?
Pretty
In
much
this
what I just
question?
said, but in a
Okay.
not so long-winded way.
So so this 5, number 5 goes with number 4. So it's kind of a follow-up on number 4.
Yeah, yeah. You could, yeah. I mean, you could use it for all 1 through 4, but I think it really more applies to 4 than anything else.
And number 2, it's just the cost, like $2,000 cost today, and then whatever is the weighted mean of the freights.
Yeah.
That's okay.
Yeah. So if, like, if you got the mean number of freights was, you know, 3.5, then it'd be 3.5 times 2,000, and that would be your estimated cost.
Okay. I thought that was simple.
Yeah.
There has to be
Well,
something I'm not doing correctly.
no, it is a very simplistic way, and that should lead you to think that it's probably not an appropriate way to estimate the average, which is what number 3 asks you about, and then discuss why or why not.
Okay.
What else? Sorry, somebody said 4.94. So let's see, 4.9. I forgot to I opened the wrong one. Questions, dummy. Okay. 4.94. Okay, so the first thing you have to do is run a normal quantile plot to assess whether or not this data appears to fit a normal distribution, i.e., does it seem likely that it comes from a population that is normally distributed. And so in SAS, we can run a QQ plot, you know, probability plot, fairly easily. It's in the SAS how-to guide. So if you go to our Google folder, right, and go into the SAS folder, and then bring up the how-to guide, the QQ plot, I believe, is in week 3 right here, quantile plot. So that's how you would run it.
Got it.
So that's the first part. That gives you the quantile plot. And then the second part, compute the correlation coefficient and p-value. Well, that's just a matter of running correlation on this. And if you actually run the regression analysis that gives you the scatter plot, if you run that one, it gives you the correlation coefficient, right? It gives you R, but it also spits out the p-value. If you take the data and just run the correlation analysis in stats, so if you go to task and utilities, and if you just run correlation analysis here, that's just going to give you R. But if you run actual regression analysis, then that gives you both. So I think it's linear regression here. If you run this one and do the scatter plot, I think here you can ask for it to display the data, and then I think it gives you that. All right, play around with some of the options.
Dr. McBride,
Yeah, Christina.
I think I got that when I actually ran the the quantile, and then I just asked it to plot the scatter plot.
Oh, when you run the quantile, did it give you the p-value that way?
Let me
Okay.
double check.
Maybe
Because
that's what it
I
was.
have it, and it pops the statistics, right? I can't remember, it was either the scatter plot. I think I did the quantile and then just asked it to plot.
Okay, yeah, I couldn't remember. I thought it came, I knew it came from one of the plots. If it comes from the quantile, then you're good to go. If not, I'm pretty sure you can get it out of the linear regression scatter plot as well.
Yeah, I
can.
also did QQ quantile plot.
And
Okay,
then just ran the scatter plot, and then you got the p-value in there. Is that what you did?
I just did you followed the instruction like the code and did QQ plot, and there was normal. It's on the QQ plot itself. There is a correlation coefficient at the top, and then also p-values. So I
that's
use
right.
those.
Okay, that's where it is. Thank you. That's right. That's where it is.
Thank you so much.
Yep. All right, what else? All right, let me just run through these really quick to make sure everybody understands them. These are all pretty straightforward, cut and dry. This one takes a little bit. The first three parts are really super easy. Part D, you have to kind of work backwards a little bit, right? So visually speaking, part D is asking this. It says, all right, here's my normal curve, right? Here's the mean, right? The mean is always right in the middle. That's mu. That's a terrible looking mu. Then they want you to find an interval, right? And this mu, remember, is 250, right? So this is 250 right here in the middle. They say if you go up a certain distance, right? So if we go plus k, so right here would be 250 plus k. So some distance k, get that cut off, and then go the same distance below. So this point here, right, is 250 minus k. So if let's just say k equals 30, then this would be 280 and this would be 220. The idea is that the area in between these is 60% of our data. Okay, well, if this is 60% of our data, we know there's 40% left over. So how much is in this tail right here? Right, just the yellow bit is how much data, what percentage? Come on, who's afraid to not be wrong? Or not afraid to be wrong? All right.
It's 20%.
Thank you, Christina. 20%, right? Because if this is 60, we know it's 100 everywhere. So 100 minus 60 is 40. So we have 40 left over. We know the normal curve is symmetrical. So half is here and half is there. So 40 divided by 2 is 20. So it's 20% here. So that basically tells us that this cutoff, right, we could find an X value right here that has 20% below us. Well, what part or what function do we have that we can give it a percentage and it will give us an X value? That's this one here, the quantile function. So you would give it the 20%, you would give it the mean, you would give it the standard deviation, you would run it, and that would basically spit out a number, and that number would be X. So let's say that number comes out and it's 220, like I said. Well, then you go 250 minus K equals 220, do a little simple math and go, K is 30. So you've just found K, right? So that's how you find K for that one, is you have to do just a little simple algebra, so to speak, solving for K. These are all simple, cut and dry, right? These are all just using the normal CDF functions and calculating things, just knowing obviously that if we're doing greater than, it's one less than, right? So one less than, one less than. Less than is you just run it. And then in between, remember, you have to run each one. So you run the CDF of 600, you run the CDF of 450, and then you do the 600 minus the 450, and that gives you the in between. What score is required to be invited to the society? Well, that's the quantile function, remember, because the quantile function gives you a score based on a percentage, and the percentage they give you is being in the top 5%. But if you're in the top 5%, you got to realize that the area below you is 95%. So you would run a quantile on 95. This question is just poorly worded. They want you to find one score, not two, one score, one X value that separates the top 75 from the bottom 25. That sounds like two different things, but it's not, because if you're on the normal curve and you've got an X right here that has 75% of the data below it, the top 75, then there's 25% below it, the bottom 25, right? So there's just one value that cuts off your curve and has 25 below, 75 above. What do we call that? All right, what do we call that value?
Lower quartile.
Yes, exactly. Lower quartile or Q1, whichever one you want to call it. Then for 479, again, these questions are just like these questions as far as you're calculating greater thans, in betweens, and then a percentile. So that's just like, you know, this one. The only difference is now you're doing a random sample of 20. So according to the central limit theorem, the mean stays the same, but remember the new standard deviation is the population standard deviation of 130 divided by the square root of your sample size. So all you got to do is take 130 divide by the square root of 20. That becomes your new standard deviation. And then you run everything, you know, like you did in the previous examples. Just know that if you want to stay as precise as possible, which is always nice to, you know, try and be precise, when you run these things, you can actually set your standard deviation to be 50 divided by SQRT of 20, sorry, not 2. And that mathematically divides by the square root of 20. So if you did that, it would keep it more precise than doing 50 divided by the square root of 20 in your calculator and then plugging it back in. Now I know the question, I don't think it was a standard deviation of 50, it was 130, but I'm just telling you, you know, as an example, instead of doing 130 divided by the square root of 20 in your calculator, you could just write as S equals 130 divided by SQRT, right, of 20, and it'll do it that way.
I was going to ask you how you did that in there, because I actually kept like 5 decimal points on it and just kept typing it in.
Yeah, this is much cleaner and
Which
easier.
is much cleaner and less painful.
Yeah. And if you're doing stuff in StatCrunch, it's the exact same thing in StatCrunch that they do. SQRT means square root in there as well. Let's see what else. This one's pretty straightforward. Just again, the wording of the questions can be a little tricky, right? They say, if a patient's systolic readings during a given day have a normal distribution with a mean of 160 and a standard deviation 20. Okay, so that's easy. We've now defined what our normal curve is. We have a mean, we have a standard deviation. What's the probability that one single measurement will fail to detect that the patient has high blood pressure? Well, you have to understand, what does it mean to fail to detect? Well, up here it says, if their blood pressure exceeds 150, they're considered to have high blood pressure. So if it fails to detect high blood pressure, that just means the reading you get has to be less than or equal to 150. So you're basically just running this scenario of a mean of 160, a standard deviation of 20. What's the probability that one measurement is 150 or less? And then for part B, what about 5 measurements? What's the probability that the average is less than 150? Same exact question, only now we have to augment the standard deviation and divide by the square root of 5, because we're now taking 5 measurements. Then the last one, how many measurements will be required so that the probability of failing to detect that a patient has high blood pressure is at most 1%. Well, now for this, we have to use the formula for sample size formula, and solve for sample size, right? So basically we're solving for a z-score for sample size. So this one requires some algebra, because you have to use the sample size formula and work backwards with that. And then this one's pretty easy. Just the one thing that people screw up is the fact that A and C have 2 answers, because first you're calculating the exact probability using the binomial, then you're doing an approximation using the normal curve. Again, down here for this part, you're doing the exact probability using a binomial, and then you're doing a normal approximation. And then the other thing that screws students up is, again, when you're working with binomials, you have to realize that if you want y to be strictly less than 5, then with a binomial, you only want to count up 0 through 4. Same thing here. If y is strictly between 8 and 14, then that means you only want 9, 10, 11, 12, and 13. So that's going to tell you, which values to use when you're doing your binomial CDFs and those kinds of things. And then you have to remember, how do you do the normal approximation, right? Do you add 0.5? Do you subtract 0.5? That's where you want to draw a picture and figure out which number gets 0.5 added, which number gets 0.5 subtracted from it, and then you do the normal approximation that way. And then we've already talked about that one. So that's everything. Any questions?
Not on this, but I do have one final question on the final project.
Go for it.
When you do the histogram distributions, and I did take your suggestion and ran them as bar graphs. I did them both, but then I think the bar graph separates. It's a little easier to see it. But those are like, what I got looks very skewed. So when they're skewed like that, they're not normal distributions. Is that correct? So you would not expect like a certain proportion, like you wouldn't expect that to follow the rule of 68%, 95, 99%. Is that correct? Like when you have a significantly skewed distribution?
Oh yeah. The 68, 95, 99.7 only works when it is very, very normally distributed. Okay. So any kind of skew, even a slight skew, is going to screw with those percentages.
Okay, because when I did the analysis, I actually did the analysis, like I always call it the golden rule, but I don't think it is the empirical rule. The empirical rule. Yep. I did the analysis of the skewness based on the empirical rule to show just how the data sat, outside the 3 standard deviations, which that when you have that many outliers outside of that, that kind of tells you the skewness. But I just wanted to make sure that those wouldn't be. I didn't think they would be, but I was just confirming. Okay.
Yeah. They're all very skewed.
That's all I have. I have no more questions. I'm sorry. I didn't monopolize most of the class tonight either. So.
No, you're good. Donna?
So in number 1, I watched some of your older videos, and I calculated the weighted mean and mean for all the 3 probability: family per parish, number in family, and then drew the histogram.
Yep.
And histogram was percent versus fright, or percent versus family per parish. Is that what I was supposed to do?
Person or percent?
Percent.
Yeah, yeah. So yeah, your histogram should basically be just, you can do it as frequency counts, but percentage, they're going to be the exact same shape, whether you do frequency or percentage, because that's just how histograms work. So either way is fine. Percentages is usually what people do because it makes more sense to people to see, oh God, that's 30% of my data rather than that's 5 things, right? So it's kind of, percentages are usually more elucidating than frequency counts, but either is fine because either is going to give you the exact same shape. The one thing I do want to remind everybody, especially in some of my older videos where we hadn't figured this out, because for the longest time I could not figure out why SAS was giving us the wrong standard deviation when we run the standard deviation on our data for question 1. And so I put this in here because one of my previous students, who's much smarter than I am, figured it out. So read this, make sure you do what is said here to switch the options around. So when you run the statistical analyses on those probability distributions for, you know, the 3 variables, it will calculate the standard deviation properly. If you don't do this, you'll get the means correct. It just, the standard deviations are all wrong. So you have to change these options, and then it finally gives you the correct standard deviations when you run it. So just an FYI, please do that so you can get the correct one. Because if you do it in Excel, you know, by hand, because you can calculate the standard deviation of something in Excel very easily, right? So for instance, it's a very simple formula right here where you just take the probability times the value minus mu squared, and then you sum them all up and then take the square root, and you can get it very easily in Excel, just kind of like you drag and drop and, you know, do some things. It's just some simple formula writing in Excel. But it's nice to actually get, you know, SAS to do it for you too, and this is what you have to do to make it work.
Okay, thank you for pointing that out. I'll go and double check.
Yeah, because it doesn't default to this. So if you just ran it in SAS, I guarantee you it gave you the wrong standard deviation. You have to go into the options tab and change these things around so that it gives you the right answer.
Okay, because yeah, as I said, I didn't have anything to compare it with. I just did in SAS, and I'm sure, yeah, I did not change any of the options for.
Yeah, it's kind of a bummer that the default isn't the way it should be. I honestly don't know why you would ever do it the default way, but yeah.
And for part 2, you just want us to rank judges based on how we want, like what we think is the best way to rank. So
Yeah,
there's no right or wrong way, as long as we are able to
as long
state
as
our
you justify it.
decision.
Yeah, as long as you state the decision you use and then justify it. You know, so as long as the numbers that you're showing in your Excel spreadsheet are, you know, your ranks match what you rank them correctly mathematically based on the criterion that you set. So if you want to rank them based on this rule, then as long as your ranks are calculated using that rule, you're good to go. Like, you can't say I'm going to rank judges based on their probability of having a case being appealed, and then you go and rank them based on the probability of having it overturned. You see what I'm saying?
Okay. And we can have multiple criteria, right?
Absolutely.
It doesn't have to be one. Yeah.
Sure.
Dr. McBride, just to confirm, I think I did it right, but you said when we do the summary statistics, you just want to select like families per parish, and then you want to weight it by the probability, families per parish probability, right?
Yes.
Is that correct? Okay.
Yes. Yeah.
Thanks.
And then make sure that you change the options so that you get the correct standard deviation. If you follow these instructions just word for word, it'll show you how to do everything. And this is just at the bottom right, of our SAS how-to guide. All right, anything else? All right, it's been a good course, Vandana.
No, just wanted to say thank you.
Oh,
Your old videos, they were very helpful, and these bi-weekly sessions were